Hello everyone, this is Previshika. So today we'll be explaining about a concept from cryptography called as zero knowledge proofs. So for explaining this concept today, we'll be going ahead with 5 different approaches. That is, I'll be explaining this concept in 5 different levels of complexity. That is level 1 for a toddler, level 2 for a teen, level 3 for a high school student, level 4 for a college graduate student, and in the final level, we'll be seeing the perspective of this topic in terms of an expert or a PhD scholar who has already done many research and is well versed in this concept. So today we'll be having a thorough understanding of this concept theoretically. Before starting with the levels, let's start with the introduction of the zero knowledge proof. So here is a basic definition. A zero-knowledge proof is a way for a prover to convince a verifier that some statement or something in that case is true, and yet reveal no additional information beyond the fact that the statement is true. So, this is what makes zero-knowledge proofs so powerful. They prove a fact without even giving away the secrets. So this technology is already put into use in ledgers in blockchain technologies and also used in cryptocurrencies, which shows its practical importance in our day-to-day life. So yes, this concept has a very useful purpose in our day-to-day life, and hence it is exciting because cryptocurrencies and blockchains are growing in demand day to day. So this is the introduction of zero knowledge proof. Let's move further and dive deep into it. So let's start with the level 1 explanation. So here I'll be explaining it as I would explain it to a child. So I'll be doing it in layman terms in short. So here, to simply explain this, we'll have to imagine a photo full of penguins wherein a puffin, that's another kind of animal or a Waldo in this case, is hiding inside it. I know where the puffin is, but I don't want to tell you where exactly its location is inside the photo full of penguins. So I can tell you I know it. How do I even convince you that I know it? How can I make it how can I trust how can I make it trust how can I make trust to you by saying that I know it? I have to prove it to you in some way, right? But I can't tell you the exact location, but still I'll be proving it to you that I know the location and you'll be convinced. That's where we'll be using the concept of zero knowledge proof. So for this, we will be taking a cardboard and put it in front of the picture with the penguins. And of course, a puffin is hiding inside the penguins. So I'll put the cardboard and I will drive a small hole amidst the cardboard, wherein through the hole I will ask you to come and see the picture. You will be able to see the puffin now, but you don't know in what direction the photo is behind the cardboard. I might have kept it in such a direction that when you come and look it through the hole, you can see the puffin. Now you are convinced, right? Because you can see the puffin. And you can trust me now that I know the location of the puffin exactly. But you still don't know where exactly the puffin is located inside the photo. You don't know its exact locations. Or in terms of cryptography, you don't know the whole details of whatever message you are going to send to the receiver. So here the key takeaway we can get is I am a prover and I have convinced you, that is, you are the verifier in this case, that you're going to verify whether whatever I'm going to say is true or not. So I have convinced you that the puffin's location is known to me without even revealing the exact location to you because you have seen the puffin through the hole. So yes, the verifier has been convinced by the prover. This concept, this technique is known as zero knowledge proof. This is a very simple example. This can be put into use or this can be extended to cryptography. And we'll be seeing how in the later levels. Let's go to the second level. That is, I'll be explaining it in terms of a middle schooler. I'll be explaining such that even a middle schooler can understand this advanced concept. And yes, this is an advanced concept and it's not even put to use in in large scale nowadays. It's just in the testing phase, maybe. It's put to use in cryptography or in cybersecurity, but it's not done in a large scale because this is an absurd concept, maybe, because it can be done only with interaction between two people, and also this needs a lot of testing for accuracy. There are a lot of use cases for it not being deployed yet. I'll be talking about that as well. Let's move ahead with the level 2 of explanation. So here we will be using a password like example. So now think about passwords. Usually if someone hacks our computer, they get to know our password. But while we use zero knowledge proofs, we could prove to you that your password, or you could prove that you know your password without even actually revealing it to anyone. It's very simple. You are going to prove your password, that you're going to prove to me. Let's say I'm the verifier, you're the prover. You're going to prove that you know your password without even telling it to me. And I will be convinced that you are aware of your password. But still, I'll not be able to decode your password because you won't be revealing it to me. That's the essence of zero knowledge proof. So from the video I have referred, Chelsea is a verifier. So the prover has convinced the verifier about the password. So he is given an example saying logging in securely without revealing password to the hacker or the computer itself. So simply while logging in itself, we are not saying this is uh, a password I'm going to use. The computer doesn't know, the hacker or the third party server doesn't know. So this is where zero knowledge proof is a proof to a statement. You don't show them why or what, you just show them a tiny segment, or just do some sort of weird magic trick that not really is a magic trick, and they will be convinced. So basically, in a magic trick, when the magician does something, the viewer will be applauding because of his magic. He'll be doing something behind the scenes that only he will be aware of, but the audience will not be aware of the trick. So that's where we say zero knowledge proof is also a kind of magic trick. So this could majorly be used in this case to increase trust without sharing secrets that could be stolen. Moving ahead to the level 3 explanation in terms of a high school student. This is a very simple use case that can be put to use even right now. Combination lock example. So imagine proving you know a combination lock's code without telling me the code. You could open a locked box containing a secret note that I wrote. By opening the box, you prove that you know the combination to open the locked box. But I learned nothing about the code itself. I'm not aware about what code you used to open the box. This is the essence of zero knowledge proofs again. You prove the knowledge of something without even revealing the secret behind it. It's like a mathematical trick that works in computers and in secure communication. And yes, it is put into use in encryption. And instead of physical locks, we can extend this understanding to encryption. Moving ahead to an explanation for an undergraduate student. So before moving ahead, we'll see what are NP completeness problems. And NP complete problems are a set of problems that can be that are actually a set of complicated problems that are handled when we know the exact solution for that problem. We should know all the core principles or the all the nitty-gritty details for solving the problem. Such kind of solutions doesn't exist, right? Like a perfect solution for a hard problem, that doesn't exist. So yes, now we can use zero knowledge proofs, and we can use zero knowledge proofs to use it to prove hard problems like NP complete problems. Let's see how. I'm going to use an example over here, which is 3 map coloring. So, or a map 3 coloring problem. So map 3 coloring problem goes like this. Let's say I have a board, and the board is divided into divisions such that each division is a map or is a country. This whole board is a map. Let's assume it. So now I have filled the whole board with a valid coloring pattern. The pattern is such that no two neighboring countries share the same colors. Yes, so here if I put green, it should be red over here and it should be blue over here, and here it cannot be blue again, it should be red. Because here it's green, it can be red only. It cannot be green, it cannot be blue because its neighboring countries are blue. This is the use case, or this is a type of NP complete problem. So how am I going to use this to prove the zero knowledge proof? So what I'm going to do is I'm the prover now. You are the verifier. I'm going to keep the envelopes filled with the colors, that valid colors that are going to be used in each country. The verifier doesn't know, that is you, will not know what colors I have placed over here because I have placed it inside a closed envelope for each country over here. Okay, so now I'm going to ask you to pick random two countries and see if the coloring is valid. So now for example, if you pick this country and this country, and suppose we have red color over here and we have green color over here, the condition is satisfied, right? But that's not all. We have to see for the entire board. Yes, NP complete problem in the sense it should be satisfied for the complete problem from the starting till the ending. So this is the first scenario, or this is the first use case, or in a train of loops. In the first loop you get the coloring right, so you will now have maybe a 5% trust on me that I have given the valid coloring inside the envelopes. Now again I will ask you to turn around maybe, and then I will shuffle these envelopes such that still it is valid. You will not believe me. Of course, you don't have to believe whatever I say. You are going to verify it again by again picking random two countries. Say now you pick these two countries, and you pick these two countries and see if they are having the valid coloring or not. You open the envelope and see red color over here, and over here you see green color. Again, it's valid, right? This process can be done for multiple times, maybe 1,000 times or so that the trust on me can be increased now. What is the trust you are going to increase upon? I have said that I have put valid coloring over here, and you are going to trust me because you have put in the process of opening random envelopes of countries multiple times, and all those multiple times it is having the legit coloring and it is following all the rules. So colors are put inside the envelope and the verifier starts randomly checking the pairs to different colors. This is the use case. Yes, this is a probabilistic approach because this is based on probability. You may not get valid coloring, you may get valid coloring. But now, as you've got valid coloring, you are now convinced that I am telling the truth. But till now, you are not sure about what are the colors for each and every country in that map. You only have a vague idea about what color might be over here, over here, over here. That is a probabilistic approach. So I have satisfied or verified your doubt about what color or what color is there in each map or each country in the map. I have convinced you that whatever coloring I have done is true, and you are convinced. This is the essence of zero knowledge proof in NP completeness problems. Moving ahead to the final level of explanation, seeing in terms of an expert. Yes, so this talks about the advanced concept and applications that can be put into use for zero knowledge proofs, using zero knowledge proofs. At the research level, zero knowledge proofs enable proving that you behaved honestly, say signing an encrypted document using a digital signature or whatsoever in that case, without even revealing the document's content itself. You trust that document is legit and you sign the encrypted document. Only the person who has encrypted the document knows the exact content of the document. But you, as a verifier, trusts the prover, that is the person who encrypted the document. You trust him and then you sign the document. And this is another example. So this kind opens new possibilities like proving ownership of cryptocurrency without even revealing your wallet. Zero knowledge proofs are not just about efficiency. They allow things we previously thought that was impossible. Yes, even the definition of zero knowledge proof sounds impossible and kinda sounds weird because we can't prove to someone without telling them everything about what we are trying to prove. But zero knowledge proof gives the way for it. So future directions with zero knowledge proofs include non-interactive proofs combining with multi-party computation for privacy and developing quantum resistant proofs. These advances can build trust in systems where people don't trust each other, such as during election times, wherein you'll have to give the count of the number of votes and you'll have to say the winning party, but you can't say who are the people voted for each and every party. Those details are confidential, you cannot give it to everybody. But you say the numbers, and the people who hear the numbers trust you. So that's an example of zero knowledge proof. This system is where we can put zero knowledge proof into use, and then we can enhance the trust between the hearer, or the prover and the verifier. Or we can use this in data privacy as well. Summarizing the whole document or the whole zero knowledge proof we have studied till now. So, to summarize, zero knowledge proofs allow convincing someone that a statement is true without revealing any of its underlying secrets, we can say. This is counterintuitive. Yes, it sounds counterintuitive or weird because it uses randomness or probabilistic approach, and it also involves interaction between the sender and the receiver, or in this case the prover and the verifier, unlike classical proofs wherein only the sender is necessary enough for proving the proof or for encrypting the document. In that case only one user is enough, but for zero knowledge proof to be valid we have to have one-on-one interaction. Zero knowledge proofs are crucial in blockchain security and privacy preserving technologies. It can be put into use in these kind of technologies and enhance the reliability of trust. From theory to practice, zero knowledge proofs are transforming how we build trust and privacy in digital systems. So, yes, that's all. Thank you so much for watching the video. I have used this video's references from a Wired interview with Professor Amit Sahai. Closing this video with a quote: zero knowledge proofs change the game. They allow us to prove things without revealing secrets. Thank you.